Hi everyone. Today what we're going to do is take the interesting definite integrals that we evaluated in the previous video and use them to derive another unexpected and kind of interesting result. And the things we evaluated last time were what I called I of z and j of z, where z is some complex parameter, and these functions are the integral from 0 to pi over 2 of sine of t to the power of z over sine of t to the power of z plus cos of t to the power of z with respect to t, or the same thing but with a cos instead of a sine on the top. And we found that these things are both equal to pi over 4. And so what I want to do is basically a substitution to transform this I of z into a different integral and see what happens. So let's take our I of z, and that's the integral from 0 to pi over 2, and I'm just going to divide the top and the bottom by sine of t to the power of z. So the top is just going to be 1. On the bottom we're going to get 1 plus cot to the power of z of t. Okay, and this is with respect to t. And we know that this is still pi over 4, and we haven't changed anything. So now, because we've got this cot of t here, why don't we try the substitution, letting u be cot of t. Alright, so what this also implies is that, well, if we do this substitution we have to change our dt into a du. So it's a kind of standard trig result that when you differentiate cot you get minus cosec squared. You can show that using either the product rule or the quotient rule, and the fact that cot is equal to cos over sine. But for now I'm just going to quote that and say that du is minus cosec squared of t dt. And we can go one step further and use a trig identity that cosec squared is 1 plus cot squared. You can derive that by taking the identity sine squared plus cos squared is 1 and dividing everything by sine squared. So anyway, we can replace the cosec squared with 1 plus cot squared, but cot is just u. So this whole thing is just 1 plus u squared dt. Now let's write our transformed integral. So this thing is the same as, we've also got to change the limits, right? And so when t is 0, what is cot of 0? Well, the way I think of it is I know that tan of 0 is 0, and cot of t is 1 over tan of t. So if tan is 0, cot is going off to infinity. So we get an infinity as our lower limit. And similarly, when t is pi over 2, cot of pi over 2, well, I know tan of pi over 2 goes off to infinity, so this should be a 0, since cot is 1 over tan. And when we do the substitution in the integrand, well, we just get a 1 plus u to the z here, right, because cot of t is just u. And the dt becomes, from this relation here, the dt is just minus du over 1 plus u squared. Okay, and so what's the conclusion? Well, we still haven't changed anything, we've just done a substitution, so we can conclude that one last thing I want to do, by the way, is get rid of this minus sign here and flip the limits of the integration around. So we're going to get the integral from 0 to infinity of du over 1 plus u to the z times 1 plus u squared. This is just pi over 4, right? And this applies for any complex number z. Okay, and you would find if you started with j of z and did a similar procedure except divided by cos to the z instead of sine to the z, you would end up with 1 plus tan squared on the denominator. Then you could do a similar substitution and you'd find actually you get to exactly the same result, right? It's equivalent. So I'm only going to talk about the I of z case for this video because it's entirely equivalent. Alright, so this is another result that I find quite interesting, quite surprising, right? We can raise this u to any complex power and do this integral and always get back the number pi over 4. So hope this has been interesting for you as well, and see you again soon to do some more maths or physics.